Hi guys. Today we're going to do a greedy algorithm, uh, and we're going to use that algorithm to solve a fractional knapsack issue or a common problem that they have, um, where you have a knapsack that has items in it. Each item can be broken down by weight and value, and therefore you can create a fraction out of it. Um, for example, you have a knapsack that has a capacity of 10 pounds. An apple is a pound, just hypothetically, and it's worth $5. You can put 10 apples in it, and the knapsack is worth $50. Similarly, if you put uh, a box of almonds in it, that's worth 2 pounds, but it's $20. If you put five of them, you have the knapsack is valued at $100, right? So you have two different possibilities, right? Um, you could put a couple of bags of almonds and fill up the rest with apples. In order to calculate that dynamically, uh, we use the greedy algorithm. Um, Basically, a greedy algorithm is a strategy, right, for best immediate choice that you make in each step. And you hope that it's the best step and you can't go back. Typically, when you go, you take a global choice in that, right? And its big O efficiency is n log n, basically, and with log being the exact opposite of a square, right? So log base 10, 100 is 100 to the power of 10, which is 1,000, right? Um, so that's the way to do it. So that's what the mathematical efficiency is of this. Uh, when you get closer and closer to solving. So as the magnitude of the input increases, that's how quickly the algorithm does its computations to give you an output, right? Um, its optimal usage is in the Huffman compression that we've already covered. Um, and we built a Huffman table and we looked at basically like whatever, like we passed in a couple of strings to our C program. And each alphabet, we looked at how often that alphabet was and we printed out the frequency. That was the Huffman encoding that we did. You can run it right here and you'll be able to see it over here. We passed in like, I think apples and bananas or something. Can't remember what it was. Yeah, bananas and apples. And we got some numbers out for it and stuff. So that's that, right? So what exactly is the fractional knapsack problem? We have a list of items. Each has a value and a weight. The maximum weight capacity of the knapsack is also given. So 50, 60, 10 pounds, whatever, right? Um, the goal or the output of the algorithm is to maximize the total value of the knapsack, right? So X number of almond bags and apples combination for the weight to hit 10, 20 pounds, 50 pounds, depending on the capacity of the knapsack, making the knapsack its most valuable. So that's the goal, basically, that you want to do. And the fractions are, 3 and 2 combinations, basically, that you can put into the knapsack. So that's what it is. So there's steps for the algorithm, right? So that we're gonna program. So I'm gonna knapsack. I'll go steps fractional. This has the Fractional Knapsack breakdown. It has an actual program written here in a bunch of languages. You have one in Python. You have it in Java, C#, JavaScript, right? So that's basically the breakdown of the program, right? That you can peruse when you have some time and you look at it. I would suggest that you just code along with me and don't type that fast, so you can easily keep up and just develop it on your own. Because the best way is to write a program, create a CMake file for yourself, because that's what I'm using. But it's really up to you, right? How you want to compile it. You can run it on you can make an output file on the console with a simple Google, like how to run the C++ file, because most systems are bundled with C++. You can download it as well. So put like a location to C++. Depending on the platform you're on, if you're on a Windows or a Mac or whatever, you can download that. Oh, don't download it, just give me the link, dude. That's dev CC, that's all I want. Oh, come on. Oh, here we go. Here's oh, you can also use it on VS Code if you want. So I've used it on VS Code. I know for a fact it's really awesome to run it on VS Code with the C++ extension that they have. Right, so you can do that over there. So anyways, let's go over here. Let's close this. What are we going to do? Okay. Okay. So that's the file. What do I do is go over here. Right. So you have this right here. So the way we want to build this, right? We want to create a data structure first things first. To create the data structure, we're going to import some statements, right? So if you guys remember, should copy them because I'm lazy. Do we need algorithm vector and IO stream? So we need all of this stuff right here. And you can see it's for to input and output, do input output stuff. We need a vector to create a data type that I was talking about. And we need an algorithm to sort that data type, right? Set data type needs to be sorted. So we put that right there. No. Why? Oh, because I'm on VS Code. I'm gonna do a VS Code shortcut when I'm not here. So. Here we go. Okay. So we're going to create a structure. Structure called item. And we're going to put stuff inside it. Like that. We'll do an end value, right? What's the other one? We're going to do weight, right? Because that's how we want to create a fraction, right? So it's going to be int fraction, right? So we're going to do that. Here. Now we're going to create the actual item, right, for the structure. So item int v int w Okay, so what is item? It's an object with three attributes that we have in it, right? And what's special about the attributes? It's a C++ constructor, uh, and it has value, weight, and fraction. Um, uh, Based on what we've already declared up here in 11, 12, and 13, right? And we want to make this a double like that, um, right? Um, these parameters right here, they represent the weight and the value of the items that we're going to place inside our knapsack, right? They're getting initialized as U and V and W on line 15, right? So we're seeing it right there. And then we're seeing setting a fraction attribute to a 1.0, which is a double, right? So we have that going over here. So that's all set. And then we're gonna go function in here. We're going to return, and here we do the math, right? So we're going to do the value over weight, right? That. And what are we going to put? We're going to put should do that. So my syntax is all jacked up, right? Should be this, should be that, should be this at the end of the line, and there's one down here. That should fix the syntax, right? And then what do we want to do, right? We want to do, since we have the structure, oh my God. What this ratio should give us, it should give us the ratio output of every object inside. So what this thing does is a ratio right, that right there. Fractional knapsack. That's the right way to do it. Okay. The sort could do main. Right. Right. This is where the vector comes in. Vector, what was it? What's these? vector. Okay, the square, the angle brackets, vector, angle brackets. Wow. Items. We'll pass in. Comma, enter, comma, enter. This is weird. Okay. Go here, go in, knapsack, capacity, 250. Okay. So we have now to do value to weight ratio sort. Okay, so we have to do sort on this thing by value to weight, and we have to calculate the ratios on them, and then on that ratio we have to do a sort. So we have to write and it's gonna do a double. Well, it's gonna return this same thing over here, which is a double. See, that's what the ratio is. So the function that takes the weight and the value and then does this ratio on that structure, it has to have the ability to return return a double, right? So we can do that. But that'll be the actual knapsack sort. So first we can do we should do a void that. So you use void when you don't return anything, right? So do value to weight ratio sort. Come in here, do this. Put that sucker in there. Okay, this is from algorithms. So go sort items. Begin. Items and begin first item, last item, empty list. All right, so the value weight ratio sort, it's a list of the items to be passed into it, right? And the sort is going to run it and it's going to sort it into descending order on a value to weight ratio, right? It's key to solve the actual knapsack, and the steps that we need in that are outlined in the link that are provided that you guys can peruse, right? So the lambda function over here, this gives the actual like order in which the comparison has to happen, right? It's a custom sort, and that's what the return is as well, right? It ensures that the items have a higher amount of efficiency, and they appear earlier in the list because of this comparison that happens between A and B, right? And you can look at this other link too. I want you guys to look at this DigitalOcean link because this is what I'm going off of over here, and this should be super helpful. Here, and you guys will see this here. Right, so what this is the general strategy of how the algorithm has to be coded, right? It reduces it to a subproblem, then solves a subproblem, right? And it makes the greedy choice. So that piece that you have right now is the part that's making the greedy choice for you. Well, I mean, it's sorting, it's creating the ratio that's going to allow you to make the choice, right? So now we can create the actual, and then we can also call this in here. Let's call what we have here. What did I call it? No. We actually on this. We're gonna feed the feed the ratio into it. So let's do that. Let's do the let's do this guy. So these are the algorithm steps that I have here. Okay, so that's the algo steps that are going to be right. So you store items. You arrange the items in descending order based on their value to weight ratio, which we've done. It initialize the total value. We've already set that, right? And then accumulate the value and iterate through the items, right? So that's what we're going to do. We're going to write an iterator, a for loop, basically. And then we're going to do if the item does not fit completely, take a fraction if and add to the proportional value. So we'll have to do if statements inside that are going to deal with the weight, because the weight is what's underneath in the fraction. If you see, right, it's value to weight ratio. So that's what we're gonna focus on, right? Well, we're gonna swap those if necessary to do the total value, and that's really that's the algorithmic part, so to speak, of it, right? So we go. Do that. This item colon items. So here, curly like that, and then we write our if statement, right? And that's the structure of the if statement, right? So inside this, we do capacity is greater than equal to item weight, like that, right? And then we go in, and then we do a self-decrement of capacity, right? So capacity that we already have, it's minus equal to like that, item weight, like that, total to see if value right there. Right. Right, so that's what this is basically. Like you're iterating through the items. You're saying, hey man, is the capacity greater than or equal to the weight that we're passing into the function over here, right? So when we call it over here, it's saying this vector is going to get passed in, right? So if we take this right here, we just go over here and just look at this for a second. What this is doing is this whole thing is getting passed in over here as this, right? And the capacity is already set to 50. So this capacity is also going to be here as 50, right? So when it goes through this, it's going to say, hey, for each one of these, so it's going to loop through these or whatever for item, in items or whatever, if the capacity, which is V and W, right? Capacity is house capacity. If 50 is greater than the weight, and what it's V and W, right? So let's put that here too. So let's do V, W, and let's just go down here really quick and do capacity, just so we know. So then we say, hey, if capacity is greater than or equal to the weight, which is 10, which it is, right? 50 is greater than 10. Then it's going to go and it's going to say capacity is equal to item weight, which is the 10, right? And it's going to add that to the capacity, so it'll become 60. And that'll be the total value, which is the item value, which is 60. So for 60, it has that weight of 60 divided by 60, and that's the fraction, right, of 1.0. So it's either going to go over here, and if it's less than, then the else block is going to kick off over here. And that's when it'll be like, if the item does not fit completely, take the fraction off, and add the proportional value. That's what that is right over here. You're adding that proportional value that's calculated to this by adding by multiplying the fraction into the value. right? So you get another fraction, and you multiply that proportion, and you add to the total value. And you do that, and in the end, you return this double value right over here. And these functions are not going to run because we have to call them both over here. And then they should work, right? So we can go double max value is equal to fractional knapsack. And then we want to pass the other function into it, which is value weight sort. Leave items. Right. Let's see how it works. Right. Included new line. Okay, and then what we do is we also iterate the the items here right, for, we can take the structure up here for the for loop. Items right here. Right. Constant items. Okay, over here. C out. C out. Item weight. Right. Value. Why is this whiny? Oh. Right. Okay. All right. So what do we have over here? We have calling both of our functions, passing the relevant items vector to it, and then for loop of the items and figuring out what the value and weight is per this that's already there, but then the additional fraction is updated by the function, right? So we're going to see that output over here. So we're going to see a very small numerical output, and we're going to see the total value of the knapsack printed out as well, which is the maximum value of the knapsack, right? So that's what we're gonna get. So let's give this up. Let's do a terminal really quick. We added it to our CMake already, so we should be able to build the file. Right. So if you go into build, the file should be there under bin. So if we physically navigate to this location and run the file, we should be able to run it. It's there, fractional knapsack. See it, maybe it built it over here in the current folder I'm in. Oh, I'm in C code file, so that's where it built it. Oh, it's not got. It's not. I've not run the. I've not run the make command. There you go. That's the bin binary search dot executable. We should run fractional knapsack. I'm going to run it this way. Okay, that's the out. That's the output. You see that 240 right there? That's the size of the maximum value of the knapsack. And the 60 weight and the 60 value and the 10 weight and the fraction taken was 1. And here the fraction taken was 1. And then the fraction was taken 6.7 for the 100 weight and 2 as well. And that's how the weights were created in order to fill up this 240 right here. So 60 and 70, 120, which will give us 120 plus 70, which is 190. And that is 0.67 of the rest of this fraction is what that space is to fill up to 40 from 190. So 60 probably. That's probably what that is. That's the number right here, 0.67 that we're seeing. So those are the fractions, and that is the best way to have an item breakdown with these vectors passed into our knapsack, right? So if our knapsack capacity, we change the knapsack capacity to 100, right? And we run this again. There we go. So the value of stuff that can be put in that is weight of 100, right? You can put in 111 of each. So 120 plus 100 is 220 plus 60 is 280, which is 280 right here that you see, right? So that's the weight of it. Cool. All right, so that's fractional knapsack greedy algorithm, right, in C++. Right, and the code to the repo is right here. Right. Thank you so much for joining. Take it easy. Appreciate your time. Have a nice evening.